So it's our really great pleasure to have Katharina from Kriegstein here today. Currently, she's head of the research group Neuromechanisms of Human Communication at the Max Planck Institute for Cognitive and Brain Sciences in Leipzig. She studied medicine and philosophy at the University of Göttingen, and then she was resident in neurology in Frankfurt and postdoc at the Wellcome Trust Center for Neuroimaging in London. In her work, she covers a whole range of central issues in human communication, including voice recognition and audio-visual face-to-face communication. So she really takes the brave step to consider the whole integrative bimodal picture as well. She's conducting groundbreaking research into phonagnosia, the deficit of not being able to recognize familiar people by their voices. And this research even made it into the Spiegel, which is the greatest German news magazine. It's very impressive because usually nothing that's interesting makes it into the Spiegel. So this was really an exceptional case. She was also recently awarded the ERC Consolidator Grant, again speaking of exceptionalism, to further illuminate the role of subcortical areas in communication and their relation to psychological pathologies such as autism spectrum disorder. So if this is not exciting enough, perhaps you should try bungee jumping or hard drugs or something. So since we as organizers are more or less all based in music communities, we're really happy to have somebody here who is deeply involved in the cognitive neuroscience of speech and voice perception. And we're particularly happy to have somebody of that impact here as our first keynote address. So without further ado, let's welcome Katharina from Kriegstein.
Yeah, thank you. Thank you very much for the invitation and for this great introduction. I'm very happy to be here and to be part of such an exciting program. So I would like to talk about how the human brain recognizes voices, and the talk will be very brain-based. So nothing with, or almost nothing with psychoacoustics. So how does the human brain recognize voices? First, let's maybe hear some examples of what voices sound like.
Ich habe nie gesagt, wenn du sagst, ich kann nicht, weil das halt...
Hi, I'm Amy, one of the available high-quality text-to-speech voices. Select Download now to install my voice.
Okay. So it's obvious that from these examples we can first understand what is said, but we can also understand, and that is on speech recognition, we can also understand how the speaker is feeling, so the emotion of the voice. And important for this talk especially is that we can get the lexical properties of the speaker, so we can understand is it the male or female voice, and we can even recognize the identity of the speaker if we know it. So this is identity. And in human brain science or in neurocognitive models of voice perception, it is assumed that these three information pieces that we get from the voice are processed relatively independently. So if we recognize these, it should be different brain regions that might interact with each other but are largely separate. And this is the neuropsychological model I just want to briefly introduce of voice perception that is currently the most prevalent one in the neuroscientific literature. So it assumes a recognition stage, and this is preceded by, of course, a perceptual analysis stage. So this is signifying the input to the brain, and then the brain has a perceptual analysis stage where there's first like a general processing of vocal sound, and then there are three separate streams already occurring at the perceptual level, where the brain extracts speech features, emotions features, and identity features. And after that, recognition takes place, and once we have recognized, for example, the identity of the speaker, we can retrieve semantic information such as the name of the speaker or any kind of other information about the speaker. So in this talk, I will focus on this stream here. I put it here separately. So basically, how do we recognize the identity of speakers? Or not how do we recognize, but how does our brain recognize the identity of the speaker? And to just give you a brief overview of the talk, in the first part I will talk about perceptual mechanisms in the brain for identity recognition. In the second part I will talk about how the brain really recognizes the voice identity. And in part 3 I will briefly talk about phonomatopoeia, which I mentioned already. So basically the question, do we all recognize voice identity? So I start with the perceptual analysis of voice identity features. And a big question, of course, also probably of someone in the audience, what are actually these voice identity features? And I cannot tell you because I think it's a very daunting problem. It depends on the familiarity with the speaker, on the speech stimulus, on the task, on the listener, on the speaker, and so on. So I will make it very, very brief here. Two important ones that have been recognized for voice identity recognition. By that I mean you hear a voice and you can say, okay, this is Kai or this is Katharina. So this I mean voice identity recognition. For these it's very important the vocal tract features, so timbre features, and to a lesser extent probably the glottal pulse features. And the reason why these are individuating are the result of anatomical features, which I just briefly show here. So this is the section, so the human head, the nose, the tongue, this is the vocal tract, and below here are the glottal folds. And the glottal folds produce, I have a picture of the glottal folds which is more medical. So this is from the laryngoscopy, and the glottal folds of course produce the carrier of the sounds. I just show you here an example. So this is a laryngoscopy of the glottal folds. You look at the glottal folds from the top.
Now give me a singing. At a low pitch and then sing up.
Because of the different anatomical features of the glottal folds of different speakers, it can be different. The second thing is the vocal tract, of course, which introduces the phoneme frequencies or filters the sounds coming from the glottal folds. And this looks like this. So this is an MRI MR imaging of the vocal tract, and what you while somebody is speaking, and what you can of course see is the movement of the vocal tract, but you can also see that, for example, the length of the vocal tract stays the same during all this movement during speech.
When it comes to singing, I love to sing French art songs. It's probably my favorite type of song to sing. I'm a big fan of Debussy. I mean, I also love operas.
So maybe to show what this is. So here it's again the section through the head. Here are the glottal folds, and this is the vocal tract. And what you can see is that the vocal tract length stays the same, while of course the articulators are moving to produce the speech sound. So, and what this does is, of course, to put speech-related phonemes in the acoustic signal, but the phoneme position also depends on, for example, the length of the vocal tract. So this here is an example for a long vocal tract, and this is an example for a short vocal tract. So one question I wanted to address in my research is where are actually these kind of features represented in the brain. And I want to present you here one of our MRI studies. So first, what is MRI? MRI is magnetic resonance imaging, and from this is the machine. You put the subject in, and then the subject does a task in this MRI machine, or it's often also called scanner. What we can get from this is a high resolution structural brain information, but we can also get functional information. And this works because we get different signals for oxygenated versus non-oxygenated blood. And it's a method with a high spatial resolution, but with a low temporal resolution. So in our MRI study on vocal features, we recorded one single speaker, and then we put the whole thing through straight, so coding software, and we derived a lot of different speakers with first, which differ just in the, we derived lots of different speakers with different vocal tract length information, and these could all also differ in the glottal pulse rate information. So the TUI could be either voiced or whispered. And then we put this all in the 2x2 factorial design with the first factor vocal tract length, so the timbre aspect, which could be either variable or fixed, and then GPR, so glottal pulse rate, which could be either voiced or whispered. So I play you, and the subjects were lying in, or participants were lying in the scanner, listening to these sounds.
No, na, na, la, ra, re.
So this is with variable vocal tract length, and this would be with fixed vocal tract length.
Lu, ga, abe, li, re.
And this is whispered. The third factor was the task factor, which I don't discuss in the result section. So one question is, where is glottal pulse rate represented in the brain? And here I show you a section of the results. This is a brain from the side, so here's the front, here's the back, and this indicates the slide that you see here. This is the front, these are the eyes, and this is the back. And in the dotted ring, it's the Hash's gyrus. It houses the primary auditory cortex and adjacent fields. And what one can see is that if participants listen to the voice in contrast to the whispered speech, we get responses here in this anterior lateral Hash's. While if participants listen to whispered in contrast to the voice speech, we get responses here in the medial Hash's. So it seems that glottal pulse rate features are processed relatively early in the auditory hierarchy in Hash's gyrus, which is close to primary auditory cortex. So vocal tract length features, in contrast, are probably processed a bit later. This is the slice here shown on this side. It's again a view from the top. Here are the eyes, and here's the back. And what one can see is that responses to vocal tract length, if that varies in contrast to if it's fixed, leads to responses in the supratemporal gyrus and sulcus. So vocal tract length information seems to be processed there. So one question that resulted from this study was, is this just like a general timbre region that reacts to any kind of vocal tract length, no matter whether it's from an animal or a human or even maybe a musical instrument. So to address this question, we did a second fMRI study. And we recorded one vowel from one speaker, and then we had one bullfrog sound, and then a musical note from an instrument. We put it again through our vocoder straight, and got different scaled versions of these sounds. And then we had a 2x3 factorial design, where the vocal tract length could be either, again, fixed or variable, but this time we didn't only have the voice, but also the scaled versions from this bullfrog and the musical instrument. So just to play you the I just play you the variables.
So, you, 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 you.
So participants were lying in the scanner, they were always pressing the button once the sequence had stopped, and they were listening to these 6 different conditions. So either the stimuli could be variable in the vocal tract length or it was fixed. And these are the results. So the main effect for just like varying in size of vocal tract length is here plotted in red. So this is the brain again seen from the side. This is the front and this is the back. And what we found, or what was the answer to our question, was looking at the interaction. So what is more active if the vocal tract length and speech varies in contrast to fixed vocal tract length, and that in contrast to the vocal tract length varying in musical instrument and the bullfrog sound. And we indeed found here a region which responds to this interaction. And here I plotted the response. Both responses, so the brain responses for the contrast, vocal tract length varies in contrast to its constant for the different conditions, and what one can see here is that in the speech condition or voice condition, human voice condition, there is more response than in the other 2 conditions. And this is present, here's just another picture of this interaction in the left and in the right hemisphere, both in the supratemporal gyrus and sulcus. So to just briefly summarize this first part, so the important identity features for recognizing and identifying human voices are glottal pulse rate, so the fundamental frequency, and the timbre, and we have looked at vocal tract length effects here, and they are processed in different regions of the brain. So fundamental frequency aspects are processed rather early in auditory regions near Heschel's gyrus, while the timbre aspects are processed a bit later in the supratemporal gyrus and sulcus. And there is a specific brain region that responds to timbre changes in the human voice. So the second part is about recognition of voice identity. So what happens? I mean, now the brain has maybe extracted these features. What does the brain do with it? And one prominent model is the so-called prototype model of voice identity processing. So it assumes that we first extract these features like fundamental frequency or vocal tract length information, and we compare that to a prototype. So this is a prototype pattern which we have stored in the brain. And this is an average voice that depends on our environment. And we then have, the brain computes the deviated features that deviate from the incoming voice to the prototype stored in the brain. And once that is done, these deviating features can be compared to reference patterns of different voices that we have stored in the brain. And if these are very close, then this distance measure here will be very tiny, and then we can identify this person. And if that the distance measure is very, very large, then it goes back here and probably will become a new reference pattern. So other indications, so this is based on behavioral results, other indications in the human brain that this kind of prototype coding occurs. So there's currently one study on that. It's from the Pascal Guillen group, and the first author is Marianne Latius. And they have tried to see whether the brain actually codes prototypes. And for that, they recorded 32 male and female voices. And they again, they also use straight. And they averaged these voices in, so that they have first the prototype voice, which is like depicted here, by averaging all these voices. And then they, the participants in the fMRI scanner, they also listened to different morphed versions. So either they were morphed between 2 of the 62 voices, 4, 8, or 16, and the they were more between the 32 voices, then it was the average voice, one for female, one for male voices. And what they found, so the experiment was passively, or listen to these voices, and then there was a pure tone in the design. Once in a while they pressed the button and they heard the pure tone. This was actually 3 experiments. I just want to show you the gist of the whole thing. They actually found that voices that are most distant to this average voice have the largest responses in the supratemporal gyrus and sulcus. So here's a view again from the top of the brain. This is a section at the level of the supratemporal gyrus and sulcus. And, this is activity that these are responses that one gets for voices that are most distant to the average voice. And this is a plot of this. So this is the fMRI response, the word response, and this is distance to mean from the voice, actual voice sample to the average voice. So this is the first indication that prototype encoding actually takes place in the brain. So, so far, all the studies that I showed, they didn't really do voice identity recognition. So it was either a syllable task or like this pure tone recognition task. So what does actually happen when we have to recognize voices when they're like in the MRI scanner? So to investigate that again with a couple of studies. Where people had voice identity recognition tasks. Let's look like this. So people were, this is a study with 2 conditions. The first one is the voice identity task. So people were seeing a screen that said speaker. They knew, okay, now I have to perform this voice identity task. And then they were listening to a couple of sentences that were spoken by different speakers. This is here in German. So this is the content of the sentence. It's called, he is dancing, he's diving, or he's exchanging. And this was spoken by different speakers. And in the speaker task, the people ignored the sentence content, but they were just supposed to say that, so they were presented at the beginning with one target speaker, so in this case it was speaker 3, and in the following block they were supposed to press a button each time they heard speaker 3, so to identify which is speaker 3, and another button if it was not the speaker, and they ignored the content. In the other task, that was the speech task, it's a control task, we had exactly the same stimulus input. So again, sentences spoken by the same speakers. But this time, the target speaker was saying the target sentence. So this is, he dances, times, and subjects were supposed to press a button each time they hear the word he is dancing, independent of which speaker the sentence is saying. So it's exactly the same stimulus input, only this task is different, and we wanted to know where in the brain this kind of task effect would occur. And okay, we also had a low-level control, which was exactly the same sentences, but it was speech and not this of these sentences. So these are the results. This is the left hemisphere. There were no responses at all in the left hemisphere, and this is the right hemisphere, and the only results that we found is here in the anterior supratemporal gyrus and sulcus, which was responding to this voice identity task in contrast to the speech task. And this is the percent signal change in the 3 different conditions. So here in the voice identity task, in green in the speech task, and this is our low-level control for the speech envelope noise. And one can see that actually the speech task doesn't activate this region more than these very low-level speech envelope noises, while the voice identity task has an increase in activation, which is an indication that this response actually really has something to do with voice identity processing. So we wanted to replicate and further look at this with, and also ask the question at what time point does this voice identity processing occur with a different method. This is MEG, magnetoencephalography, and this is the machine. So again, similar to fMRI, the participant is sitting in this machine and doing some kind of experimental task. And it measures the magnetic field that is induced by electric currents in the brain, and it has a really, really high temporal resolution. And the results look like this. One can plot them as topography, and one can also do source reconstruction to see where the currents are coming from. So we did exactly the same design as in the fMRI study, and we basically replicated this anterior supratemporal sulcus and gyrus responses to voice identity in contrast to speech task. And on top of that, it correlated with the behavior performance of the subject. So these dots all represent one subject. If they, subjects which were good at or very good at voice recognition also had high responses in this region for the voice task in contrast to the speech task. So it seems that identity representation is present in anterior supratemporal gyrus. So when I introduced or began this talk, I showed you some voice examples, and probably nobody actually recognized these voices. It was voices from unfamiliar speakers. But actually what we are most interested in when we recognize speakers are these kind of voices.
60 years ago, the planes that flew over Berlin did not drop bombs. Instead, they delivered food and coal and candy to grateful children.
Does anybody recognize? Yeah. Okay. Who is it? Obama.
Think big, because then you're going to get big. Then you're going to go and achieve big things.
Anybody recognize it? Schwarzenegger.
Wenn die schwäbische Hausfrau ein krankes Familienmitglied hat, dann muss sie dieses kranke Familienmitglied auch erst wieder gesund pflegen.
Yeah.
Okay, so these voices are familiar, and what is very different from unfamiliar voices is that we actually know the face to the voice. And one question is, or one thing is that voices are usually learned together with the face. Does that make a difference for auditory processing? So if you look at neuroscience textbooks, then you would think, okay, no, it doesn't make a difference because you have your auditory system, you have your visual system, and yeah, you recognize the auditory voice, and maybe then you remember the face or something like that. But for auditory processing, it's not important. So, but we wanted to investigate that that is actually really the case. So, is there an influence of face information when we recognize voices, for example, just on the phone, when we don't see the face? So we did an fMRI study, combined behavior and fMRI study, and the stimuli, or the stimuli and design are the following. So we trained participants on 6 different voices. 3 were learned by the voice, the name, and the video of the person. And then there was the control learning, where the people learned the voice, the name, and the symbol of the occupation of this person. So for example here, Ingus, we hear the voice, and okay, this is signifying he's a painter. And subjects were then, after this training, tested whether they made the correct association. And the training for each voice was very, very brief. So each voice was just trained 2 minutes. And after this, we had an auditory-only test. So here they had the task instruction, which was that they were supposed to identify the speaker, and then they listened to sentences spoken by different speakers. So sentences spoken by these 6 different voices, and they were supposed to say which speaker it was, so whether the name matched the speaker's voice or not. And the same for these kind of voices. And over the participants, these 2 conditions were exactly matched. So the stimulus input was exactly the same over the participants. So if you have the textbook view, you would say, okay, voice recognition after this training and this training should be exactly the same. So the performance correct should be exactly the same. But this is actually not the case. So here are the behavioral results for the auditory-only test. And this is performed correct. And in dark gray is for the voices that the participants learn with the voice and the face together. And in light gray, it's for the condition where the voices were learned together with the occupation signal. And And there's a 5% difference between these two conditions. We call this effect the phase benefit, and it has been shown with two other or several other control conditions now also, not with a symbol but just with auditory only learning in contrast to the voice-phase learning, and also voice-phase learning in contrast to voice-name learning. The voice-phase learning always works better. And one question that we wanted to answer was, how does the brain do it? Or what is actually the mechanism for why our voice is better recognized if we know the face of the speaker? And there are, of course, loads of alternative hypotheses, but I want to just go to the one that we actually thought was the best one. We thought that probably visual mechanisms are having the auditory processing. And one visual mechanism would be face regions. So here in blue I plot bold responses in an fMRI study where people look at faces in contrast to objects. And this here is a very famous region. It's the fusiform face area. It holds face identity. And we thought, okay, if voices are recognized, maybe this region is recruited as well and has the voice area to recognize the voice. And if that is the case, then actually this area should not only respond to auditory stimuli, not only respond to visual stimuli, but also if we do speaker recognition for speakers that we have learned with the face. And to test that, we again used this design. So the question is, in this speaker recognition, is this fusiform face area active in contrast to that condition, so after the symbol learning? And this is exactly what we find. So in red is now the speaker recognition after voice face learning in contrast to after voice occupation learning. So one could of course say, because fMRI has this low temporal resolution, that this is just imagery. So we recognize the voice and then we remember the face, and therefore we have these visual areas activated. To adjudicate between this perceptual hypothesis and the remembering hypothesis, we did an MEG study. And the question here is it actually this area responsive during early perceptual processing, or is it late? And if it's late, then it's probably measuring. If it's during early perceptual processing, it's probably perception. And this is again the same design, but this time optimized for MEG. So this is the top plot, speaker recognition after voice face learning in contrast to after voice occupation learning, and the maximum difference is at this sensor here. And what we can see is that there's already a difference between voice face learning here in purple and voice occupation learning at 100 milliseconds, so very, very early. 110 milliseconds after stimulus onset, we find a difference response between these two conditions. So one big question is, of course, does this locate to the visual area? And this is exactly what we find. So this is looking at the brain from the bottom. This is the fusiform face area, so the area that is always responsive for faces in contrast to an object. It's a visual area, and we find that for auditory voice recognition, it activates at 110 milliseconds, or between 90 and 130 milliseconds. So very, very early recruitment of visual mechanisms for auditory-only tasks. And this occurs after only 2 minutes of training the speaker with voice and face. So one question is, where does this get? How does this auditory information get there? If it's so quick, there should be direct connections. And we investigated this with a diffusion-weighted MRI approach. And this is the brain, and we first had to functionally localize these voice and face areas because there are no anatomical structures that actually correspond to it. So here are the 3 voice areas that I talked about. So this is the one that responds mostly to the vocal tract information. This is the one that responds mostly to prototype encoding, and this is the one that was active for voice identity recognition at 200 milliseconds. And these are 2 different localizers for the visual areas, so the fusiform face area. And our question was, are there direct connections between these areas? And indeed, there are. So in blue, again, the visual area, in red, the auditory areas. And these two areas here, I call it now computational encoding and identity coding area, they are directly connected here to the visual area. So to conclude this part, the fusiform phase area visual mechanisms help very early on in auditory processing, and they are directly connected. Visual areas are directly connected to auditory areas and help during perceptual processing of auditory stimuli. So this is with that I would like to conclude the brain part and just talk a bit about the question: do we actually all recognize voices? And to make it short, the answer is no. So for a long time, it has been known that there are deficits occurring in voice identity recognition due to brain tumor or brain lesions, and this is called acquired phonoagnosia. So phonoagnosia is the inability to recognize voices. It comes from which words? It's phone, the sound, or the voice, and agnosia, the inability to recognize. And it can occur independent from speech recognition difficulties, which has been very exciting in the 70s because it shows that there are different brain regions for speech processing and voice identity processing. And it's extremely rare. So in the neurological world, one really, really seldomly finds it. But there is also something probably that is called developmental phonoagnosia. These are healthy people that have a selective deficit in voice identity recognition. And the first case has been described by Lucia Garrido, and it is KH. So KH is her initials. She's a 60-year-old healthy manager, and she reported that she cannot recognize. You cannot recognize voices, even if she gets a phone call from her own daughter. She doesn't know who that is unless she looks at the display of the phone. She can differentiate between male and female voices. She can also recognize the vocal emotion in stimuli. She can recognize auditory objects, so whether it's a car sound or violin or whatever. And to cope with her deficit, she has developed several strategies. And these strategies in developmental phonoagnosis are very individual. So she, for example, at her workplace used a different name for herself than for private purposes. So if somebody called her, she could always say, oh, okay, if this person is calling me Jane, then it's a private relation. If it's calling me by a different name, it's a public relation. And of course, this leads to embarrassing situations. So one phonoagnostic, for example, told me that he talked to a person called Claudia, and then only after 2 minutes he realized that it's not the Claudia that he's very familiar with, but the other Claudia. So it can lead to embarrassing situations. So how many people actually have developmental phonoagnosia? We wanted to find this out and also to find more cases of developmental phonoagnosia, and to do that we developed an online test and collected, so where people could test their voice recognition. And then the interesting cases we picked out and sent them a questionnaire to get further at where does this voice recognition deficit come from? Is it more general? Do they also have face recognition deficits, and so on? And then we had telephone interviews with the most interesting cases and did an extensive laboratory testing with the 4 still interesting cases, and then there were 2 novel cases in the end of developmental phonoagnosia who really had a specific deficit in voice identity recognition. They weren't a music, they could recognize faces very well, they didn't have problems in auditory speech perception or anything like that, so they had a specific deficit in voice identity recognition. So if we compare these 2 cases with our data set, one would get at a rough prevalence estimate of 1 per mil. But there are now also other reports saying that it's probably even more prevalent than that, so between 2 and 3%. So one question is, why can developmental phonoagnostics not recognize voices? And this why can apply to different whys. So one is on the behavior level, what's actually the problem that they have? And the answer to that is that it's different, actually, even in the developmental cases. For example, here are the 2 cases. It's again the initials AS and SP. For example, AS already has a deficit in voice discrimination. So when she hears 2 voices, they sound exactly the same to her, while SP doesn't have a problem. So if he gets a voice discrimination task, then he's fine. But as soon as he has the task to associate information to a voice, such as the name or the face or the occupation, then also SP has difficulties with voice identity recognition. So while for IS, if she has, in the certain case, she has recognized the voice is familiar, then she's good at retrieving semantic information from this person. So if she has recognized one familiar voice, she can say, oh, it's this and this person. So the behavior profile, even within this community of phonoagnostic people, is different. For a long time, we assume it's a potential hereditary cause, like similar deficits, like dyslexia, developmental dyslexia. Also, people who cannot recognize the identity from faces. That it's assumed that it's a hereditary deficit. These are the families of these 2 cases, which currently show that apparently there is no evidence for hereditary deficit. So hereditary deficit, we would assume that within, so these are the different generations, these are in black, the index cases, and if it's hereditary, we would of course assume that it runs in the family. So that one of the ancestors would also have developmental phonoagnosia. But currently we don't have evidence for that. So do we all recognize voice identity? No. Rough prevalence estimate between 1 per million and 2% have developmental phonoagnosia. And developmental phonoagnostics, even within this group, there are different behavioral phenotypes. And currently we don't know the cause. If you want to help us with our research, please take our online test and check whether you're good at voice recognition. With that, I would like to end, and thanks to my group, in particular 3 people who did voice recognition research. This is Claudia Haus-Wandelwitz, Helen Blank, and Sonja Schall. I would also like to, and this is our group, my collaborators and my funding organizations, and thank you very much for your attention.
Thank you very much, Katharina. Any questions? Everyone, 5 minutes?
Well, first, thank you for the talk. It was very interesting. I have a question about the first part, the perceptual identity. Stimuli. You talked about different vocal tracts, and then there was this experiment with different vocal tracts and different bullfrog like variations in the instrument. And I was wondering if the different vocal tracts, was it different speakers with different vocal tract lengths, or did you process the stimuli with straight?
Yes, so it was one speaker, and we processed it with straight, so that only the vocal tract length was different between the speakers. Everything else was the same, because it was recorded from the same speaker, and then processed with straight.
I was thinking it would probably be interesting to have different speakers, because if you can't really guarantee that everything else is the same if you process the sound. right? I mean, the processing can alter also other.
Yes, for that we introduce control conditions where we also use the processed sounds, but where, for example, the size doesn't vary, but the sounds are the same. And also, if you, so for example, with a bullfrog, if you have, so basically you could take the bullfrog as a different speaker. These are also processed sounds, and if we vary in the condition where these processed sounds vary, then if that changes anything else besides vocal tract length, then this controls for the other changes besides vocal tract length and processed sounds.
Right, but for the musical instrument, for example, the mechanism, the physical mechanism is different. So processing the speech and processing the musical instrument with the same type.
With straight, you mean if you apply
well, yes, yes. Like playing different notes on a clarinet and processing like different lengths of the two doesn't really give exactly the same result.
But if you put it, the same, so if you put a bullfrog or a clarinet sound, let's say that, and the vocal tract, the voice sound through the exactly same mechanism as straight, you would assume that it's different processes.
I would propose to continue the coffee break. There are other questions.
Yeah, I had one about your face and voice one. I'm curious whether were the faces shown actually the faces of the people whose voices were used, and so is that important or not? Or can you just associate any arbitrary face and that would still work?
Yeah. So I think yes, of course we used the videos recordings, and it was the voice that belongs naturally to the face. And actually there is a really great study by Kamachi which showed that even for unfamiliar voices and faces, if you play them in succession, so as first the voice and then the face, people are over chance in performance to say whether this face belongs to this voice. So I assume that there's a natural pairing, and that actually the reason why we see this interaction is that there are complementary cues in the voice and the face, so the interaction between voice and face region, that there are complementary cues with the voice and the face that are learned for voice identity, actually also for speech, but that's then different languages, and that's the why actually this pairing works. If one puts an arbitrary face to this voice, I would think that we don't have such a large face benefit. Maybe not 5%, maybe 2% or something like that. But in theory, it should work.
In Canada on the CBC, there's certain announcers you hear all the time in certain shows. And I one time went to the radio for an interview and actually met the people, and I was really surprised at what their face looked like compared to what my creative image and
yeah, that's also one phenomenon, and I don't know whether that's something because radio presenters get selected for like very distinctive voices or something like that. Why the Kamachi study maybe just normal students' voices. So I don't know whether there might be a difference. I know this phenomenon. I don't know whether there's maybe a difference in very distinctive voices that maybe are so distinctive that one has like this imagination of the face, which maybe doesn't.
Okay, the last question by Thomas.
On the same issue of face and voice identity, how would you say, or does it extend to things? So, I mean, I know the sound of the book dropping, and I see the book. Is there a connection? Is it the same mechanism?
Yes, so there is research with very simple stimuli like beeps and flashes basically, and there are direct connections between primary auditory regions and visual regions. So what I think, or what we thought, was that it actually always, that it extends always to stimuli that are naturally connected, we tried to elicit the same visual activation with mobile phones. So for example, you have a 3 different mobile phones, or 6 different mobile phones. 3 are learned with the appearance of the mobile phone, and 3 are learned with the brand name. And we wanted to see whether actually we also find this benefit, and we didn't find it. And we also didn't find the cross-neural activation. So currently there's no evidence for if it's an arbitrary pairing, which goes back to also the question from if there's an arbitrary pairing, it doesn't seem to work so well. That's actually the evidence we have in the moment.
Okay, thank you very much. This concludes the first keynote. Let's thank Katharina.